Tonight, we're diving into one of the strangest mysteries in modern astronomy. Right now, as you're watching this, radio telescopes around the world are picking up signals from space that we cannot explain. Not background radiation, not stellar noise. Actual signals with structure and pattern. Bursts of energy so powerful they shouldn't exist. Transmissions that repeat on schedules we can measure, but not predict. Signals that arrive from specific points in the cosmos and then vanish without a trace. And the most unsettling part is this. We can't tell if we're looking at the most extreme physics the universe can produce, or if we're looking at technology. Something deliberate, something trying to reach us. By the end of tonight, you're going to understand why these mysterious transmissions might be the most important discovery in human history, or the greatest cosmic puzzle we've ever faced. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with the basics. When we talk about signals from space, we're mostly talking about radio waves. Radio waves are a form of electromagnetic radiation, just like visible light, but with much longer wavelengths. They can travel through the vacuum of space, essentially forever, without losing their structure. This makes them perfect for carrying information across vast distances. Everything in the universe emits some kind of electromagnetic radiation. Stars emit light and radio waves. Gas clouds emit radio waves as their atoms vibrate and collide. Black holes emit radiation as matter falls into them. Pulsars, which are rapidly spinning neutron stars, emit beams of radio waves that sweep across space like cosmic lighthouses. Most of this radiation is random noise. It's chaotic, unstructured, the natural byproduct of physical processes. When a star burns hydrogen into helium through nuclear fusion, it releases photons at all wavelengths. When electrons spiral around magnetic fields, they release synchrotron radiation. When atoms collide in gas clouds, they release photons at specific wavelengths determined by quantum mechanics. All of this creates a constant background hum of electromagnetic radiation filling the universe. Radio astronomers have been listening to this hum since the 1940s. They've catalogued thousands of natural sources, pulsars, quasars, supernova remnants, star-forming regions, galaxies. They know what natural radio emissions look like. They know the signatures of plasma, of magnetic fields, of matter spiraling into black holes. But occasionally, very occasionally, they detect something different. Something that doesn't fit the patterns. Something that makes them stop and wonder if they're looking at something fundamentally new. The first truly mysterious signal was detected in 1967 by a graduate student named Jocelyn Bell Burnell. She was working with a radio telescope at Cambridge University, studying quasars, extremely bright and distant galaxies powered by supermassive black holes. The telescope was crude by modern standards. It consisted of 2,048 dipole antennas strung across 4.5 acres of English countryside, connected to a chart recorder that printed data on paper. Bell had to analyze the data by hand, scanning through 96 feet of chart paper every day, looking for interesting signals. On November 6, 1967, she noticed something odd. A small, regular pulse appearing in the data. Not random noise. Not a glitch. A signal that appeared at the same spot in the sky every time the telescope scanned past. The signal pulsed every 1.337 seconds. Exactly. It was so precise that Bell and her advisor Anthony Hewish, initially wondered if it might be artificial. They jokingly called it LGM-1, which stood for Little Green Men 1. They checked everything. They verified that it wasn't interference from terrestrial sources, no nearby radio transmitters, no electrical equipment creating false signals. They confirmed that the signal was coming from space, from a specific location in the constellation Vulpecula. And they verified that it was pulsing with extraordinary regularity, more regular than any clock on Earth. For a few weeks, Bell and Hewish genuinely considered the possibility that they might have detected a signal from an alien civilization. It was the only explanation that seemed to fit. Natural astrophysical processes don't create signals with that kind of precision. Stars don't pulse every 1.337 seconds. Gas clouds don't emit radio waves in perfect regular intervals. The universe is chaotic. Natural processes are messy. This signal was too perfect. But then Bell found another one, and another, and another. Within a few months, she had detected 4 separate pulsing signals, each coming from a different part of the sky, each pulsing at a different rate. This changed everything. If these were alien signals, it would mean multiple civilizations, all broadcasting at roughly the same power, all detectable from Earth with the same telescope. That seemed unlikely. The more probable explanation was that they were looking at a new type of natural object, something that could pulse with extraordinary regularity. Within a year, the mystery was solved. The signals were coming from pulsars, neutron stars. When a massive star explodes in a supernova, the core collapses into an object about 12.5 miles in diameter, or 20 kilometers, but containing more mass than the Sun. This creates an object so dense that a sugar cube-sized chunk would weigh about 1 billion tons on Earth. Neutron stars spin incredibly fast, sometimes hundreds of times per second. Because they conserve angular momentum as they collapse, like an ice skater pulling in their arms to spin faster. They also have extraordinarily strong magnetic fields, trillions of times stronger than Earth's magnetic field. As the neutron star spins, these magnetic fields accelerate charged particles, which emit beams of radio waves from the magnetic poles. If the magnetic poles aren't aligned with the rotation axis, these beams sweep through space like a lighthouse beam. If Earth happens to be in the path of one of these beams, we see a pulse every time it sweeps past us. Hence, pulsars. The discovery of pulsars was a triumph of observational astronomy. It explained the mysterious signals perfectly. It predicted the existence of neutron stars, objects that had been theorized but never observed. And it earned Hewish a share of the 1974 Nobel Prize in Physics. Bell didn't get the prize, a decision that remains controversial to this day, but her discovery fundamentally changed astronomy. Pulsars are now some of the most precisely studied objects in the universe. Their pulses are so regular that they rival atomic clocks in precision. Astronomers use them as cosmic clocks to test general relativity, to search for gravitational waves, and to map the distribution of matter in our galaxy. The mystery was solved. Except that it wasn't. Not completely. Because while we now understand pulsars, that doesn't mean we understand all the signals we're detecting. In fact, pulsars open the door to a much deeper realization that the universe can produce signals we don't expect, signals that challenge our understanding of physics, signals that look almost too organized to be natural. And in the decades since Bell's discovery, we've detected new types of signals that remain mysterious. Fast radio bursts. That's what astronomers call them. FRBs for short. They're one of the most perplexing phenomena in modern astronomy. The first one was discovered in 2001 by Duncan Lorimer and his student David Narkovich, who were analyzing archival data from the Parkes Radio Telescope in Australia. They were looking through old observations, data that had been collected in 2001 but never fully analyzed. And buried in that data, they found something extraordinary. A burst of radio waves that lasted less than 5 milliseconds, a fifth of a blink of an eye. But in that brief flash, it released as much energy as the sun emits in an entire day, concentrated into just a few milliseconds. That's an almost incomprehensible amount of power. And the signal had a very specific property called dispersion. Radio waves travel through space at the speed of light, but when they pass through plasma, the ionized gas that fills the space between stars, different frequencies travel at slightly different speeds. Lower frequencies get delayed more than higher frequencies. By measuring this delay, you can calculate how much plasma the signal passed through on its way to Earth. And from that, you can estimate how far away the source is. The Lorimer burst, as it came to be known, had traveled through an enormous amount of plasma. The dispersion suggested it had come from outside our galaxy, possibly billions of light years away. But here's the problem. No known astrophysical process could explain it. Pulsars don't produce bursts this bright or this brief. Supernovas release enormous amounts of energy, but they unfold over weeks or months, not milliseconds. Gamma-ray bursts, which are among the most powerful explosions in the universe, release most of their energy as gamma rays and X-rays, not radio waves. Nothing in our catalogue of cosmic phenomena matched what they were seeing. For years, the Lorimer burst remained a mystery. Some astronomers thought it might be a fluke, a malfunction in the telescope, or interference from a terrestrial source. But then, in 2007, another FRB was detected. And then another. And another. By 2013, astronomers had catalogued about a dozen FRBs. Each one lasted just a few milliseconds. Each one released enormous amounts of energy. And each one seemed to come from a different location in the sky. This pattern, brief, energetic, non-repeating, suggested that FRBs were cataclysmic events. Perhaps the signal was produced when two neutron stars collided, or when a neutron star collapsed into a black hole, or when a black hole consumed a neutron star. These are all violent, one-time events that could theoretically produce a brief flash of radio waves. But then, in 2015, something changed. Astronomers detected an FRB that repeated. FRB 121102. It was first detected on November 2nd, 2012, hence the designation 121102. But it was just another single burst. Nothing special. Then, in 2015, astronomers detected another burst from the exact same location in the sky. And then another. And another. Between 2012 and 2017, FRB 121102 produced dozens of bursts, all coming from the same source. This changed everything. If FRBs were cataclysmic one-time events, they shouldn't repeat. A neutron star can only collapse once. Two neutron stars can only collide once. But FRB 121102 kept flashing over and over from the same location. Whatever was producing these bursts wasn't destroying itself in the process. It was something that could produce repeated bursts of energy, each one lasting milliseconds, each one releasing as much energy as the sun emits in a day. and we had no idea what it was. The discovery of repeating FRBs narrowed the possibilities, but it didn't solve the mystery. It ruled out some models, but it opened up new questions. Astronomers traced FRB 121102 to a dwarf galaxy, about 3 billion light-years away, or about 18 quintillion 600 quadrillion miles. It was located in a region of intense star formation, a clue that suggested the source might be a young, highly magnetized neutron star called a magnetar. Magnetars are neutron stars with magnetic fields up to 1,000 times stronger than typical neutron stars. These fields are so intense that they can twist and snap, releasing enormous amounts of energy in brief flares. This seemed like a plausible explanation for repeating FRBs. A magnetar, experiencing repeated magnetic eruptions, could produce the kind of brief, energetic bursts that match the observations. But there were problems with this model too. Not all repeating FRBs behave the same way. Some repeat regularly, like FRB 180916, which shows a 16-day cycle of activity. For 4 days, it produces multiple bursts. Then it goes silent for 12 days. Then the cycle repeats. This kind of periodicity is hard to explain with magnetar models. What mechanism could cause a magnetar to turn on and off every 16 days? Some astronomers suggested it might be orbiting another object, a companion star or black hole, and the bursts are only visible when the magnetar is oriented in a certain way relative to Earth. But this is speculative. Other FRBs don't show any periodicity at all. They burst randomly, unpredictably. And some FRBs produce just one burst and then go silent forever. The diversity of behaviors suggests that there might not be a single explanation. FRBs might not all come from the same type of source. There might be multiple mechanisms, multiple types of objects, all producing similar signals but through different physical processes. This is where the mystery deepens. Because if FRBs come from different sources, then detecting an FRB doesn't tell you much. You can't just say it's a magnetar or it's a neutron star collision. Each FRB might require its own investigation, its own analysis, its own explanation. And we're detecting more of them every year. As of 2026, astronomers have catalogued over 1,000 FRBs. Some repeat, some don't. Some show periodicity. Some are completely random. Some come from galaxies billions of light-years away. Some come from closer sources. And we still don't have a unified theory that explains all of them. But FRBs aren't the only mysterious signals we're detecting. There's another category of signals that's even more perplexing. The WOW signal. On August 15th, 1977, a radio telescope at Ohio State University detected a signal that remains unexplained to this day. The telescope was part of SETI, the search for extraterrestrial intelligence. It was scanning the sky, listening for signals that might indicate the presence of intelligent life. The astronomer working that night was Jerry Ehman. He wasn't at the telescope. Nobody was. The telescope operated automatically, recording data onto computer printouts. A few days later, Ehman was reviewing the printouts when he noticed something extraordinary. A signal had appeared in the data that was far stronger than the background noise. The signal lasted 72 seconds, the maximum time the telescope could observe any one spot in the sky as Earth's rotation carried it past. And it had a very specific frequency, 1,420 megahertz. This frequency is significant. It's the frequency at which neutral hydrogen, the most common element in the universe, emits radio waves. It's also in the waterhole, a quiet region of the radio spectrum where galactic background noise is minimal. If you were an alien civilization trying to communicate across interstellar distances, you'd probably broadcast at this frequency because it's one of the easiest frequencies to detect. Eamon was so struck by the signal that he circled it on the printout and wrote, "Wow," in the margin. Hence the name, the WOW signal. The signal appeared to come from the constellation Sagittarius, near the star Tau Sagittarii. It was narrowband, meaning it was concentrated at a very specific frequency, not spread out across multiple frequencies like natural sources. And it was strong, about 30 times stronger than the background noise. Everything about it suggested an artificial origin. A signal deliberately broadcast at a specific frequency designed to be noticed. But then it vanished. The telescope scanned the same region of sky again and again over the following days, weeks, and years. Nothing. The signal never appeared again. This is the central mystery of the WOW signal. If it was a transmission from an alien civilization, why did it only appear once? Why broadcast a signal for 72 seconds and then stop forever? If it was a natural phenomenon, what process could produce a narrowband signal at exactly the hydrogen line frequency for exactly 72 seconds and then never repeat? Over the decades, astronomers have proposed dozens of explanations. Maybe it was a glitch in the telescope. But the signal appeared in only one of the telescope's two receivers, which were pointed at slightly different parts of the sky. If it was a glitch, it should have appeared in both receivers. Maybe it was interference from a satellite or aircraft. But satellites and aircraft move, and their signals drift in frequency due to the Doppler effect. The WOW signal didn't drift. It remained at a constant frequency, which is what you'd expect from a stationary source in space. Maybe it was a reflection of an Earth-based signal bouncing off space debris. But space debris is rare at the distance required to produce a 72-second observation, and the signal's frequency doesn't match any known terrestrial transmitter. Maybe it was a natural astrophysical source, a pulsar or a magnetar having a brief flare. But pulsars produce broadband signals, not narrowband signals. And magnetars don't typically emit at the hydrogen line frequency. In 2017, astronomer Antonio Paris proposed that the signal might have been caused by a comet. Comets emit radio waves at the hydrogen line frequency when their ice sublimates and releases hydrogen atoms. Paris identified two comets, 266P Christensen and P/2008Y2 Gibbs, that were in the general area of the sky where the WOW signal appeared. This seemed like a promising explanation. But other astronomers pointed out problems. Comets move across the sky, and the WOW signal didn't show any sign of movement. It appeared at a constant position, which is inconsistent with a comet. The signal was also much stronger than what you'd expect from a comet at that distance. And when astronomers went back and checked observations of other comets, they didn't find any producing signals similar to the WOW signal. So, the comet hypothesis remains speculative. It might explain the signal, but it's not proven. As of 2026, the WOW signal remains unexplained. It's one of the best candidates for a potential alien signal ever detected. But it's also possible that it was just a weird natural phenomenon that we don't understand yet. The frustrating part is that a single detection isn't enough. In science, you need reproducibility. You need to detect the signal multiple times, study it, analyze it, confirm that it's real. One detection, no matter how intriguing, is just a data point. It's not proof of anything. This brings us to a fundamental challenge in the search for extraterrestrial intelligence. How do you distinguish between a signal from an alien civilization and a natural phenomenon you don't understand? The problem is that we only have one example of technology, ours. We know what our radio transmissions look like. We know the frequencies we use, the modulation techniques, the power levels. We can design SETI searches to look for signals similar to ours. But an alien civilization might use completely different technology. They might broadcast at frequencies we're not monitoring. They might use modulation techniques we don't recognize. They might encode information in ways we can't decode. Or they might not use radio waves at all. Maybe advanced civilizations use laser pulses, or neutrinos, or gravitational waves, or some form of communication we haven't even imagined. We're searching for signals that look like what we would send. But there's no guarantee that aliens think like us, or use technology like ours. This is called the anthropocentric bias in SETI. We're biased toward assuming that aliens will communicate in ways that make sense to us. And that bias might cause us to miss signals that are right in front of us. Consider FRBs again. If you had asked an astronomer in the year 2000 what an alien signal might look like, they probably wouldn't have described something like an FRB. Millisecond-long bursts of radio waves, releasing enormous amounts of energy. That sounds more like a natural astrophysical phenomenon than a communication signal. And yet, we still don't fully understand what causes FRBs. We have theories, magnetars, neutron stars, black holes, but none of these theories explain all the observations. There are still FRBs that don't fit any model. So, could some FRBs be artificial? Could they be signals from alien civilizations? Most astronomers would say no. The energies involved are too high. You'd need to harness the power of an entire star to produce an FRB. That's not impossible. There are hypothetical megastructures called Dyson spheres that could capture the energy of a star, but it seems unlikely. Why would a civilization broadcast signals that require star-level power? Why not use something more efficient? But we can't rule it out completely. We don't know what's normal for a technologically advanced civilization. Maybe what seems wasteful to us is actually efficient by their standards. Maybe they have energy resources we can't imagine. Or maybe FRBs aren't communication signals. Maybe they're the byproduct of some kind of industrial process, like interstellar propulsion. In the 1960s, physicist Robert Forward proposed that you could accelerate a spacecraft to relativistic speeds using a powerful laser or microwave beam. You'd build a giant transmitter, possibly in orbit around a star, and aim it at a spacecraft equipped with a light sail. The beam would push the sail, accelerating the spacecraft without needing to carry fuel. If an alien civilization used this technology, we might detect the beam as a brief, powerful radio burst every time they launched a spacecraft. From our perspective, it would look like an FRB. This is speculation, of course. There's no evidence that FRBs are artificial. But the point is that we can't assume we know what an alien signal would look like. The universe is stranger than we imagine. Natural processes can produce signals that seem artificial, and artificial processes might produce signals that seem natural. We're still learning. Another mysterious signal category emerged in 2019. BLC1. Breakthrough Listen Candidate 1. This was detected by the Breakthrough Listen project, a 10-year, $100 million initiative to search for signs of intelligent life in the universe. The project uses radio telescopes around the world to scan nearby stars, looking for narrowband signals that might indicate alien transmissions. In April 2019, the Parkes Radio Telescope in Australia was observing Proxima Centauri, the nearest star to our Sun, located about 4.24 light-years away, or about 25 trillion miles. Proxima Centauri is a red dwarf, smaller and cooler than our Sun. It has at least 2 planets, one of which, Proxima Centauri b, orbits in the habitable zone, the region where liquid water could exist on the surface. This makes Proxima Centauri one of the most interesting targets for SETI. If there's intelligent life anywhere nearby, it might be there. During the observation, the telescope detected a signal at 982 MHz. It was narrowband, concentrated at a very specific frequency. It appeared to be coming from the direction of Proxima Centauri, and it showed a slight drift in frequency over time, consistent with a source that's moving relative to Earth, like a planet orbiting a star. This was exactly the kind of signal SETI researchers hoped to find. A narrowband signal from a nearby star showing characteristics consistent with an artificial origin. The team analyzed the data carefully. They checked for interference from satellites, aircraft, cell phones, Wi-Fi routers, anything terrestrial that might produce a signal at that frequency. They looked at the signal's properties, its bandwidth, its drift rate, its duration. Everything seemed consistent with a signal coming from space. For several months, BLC1 was one of the most exciting SETI candidates ever detected. Researchers were cautious. They didn't announce it publicly right away, but internally, they were taking it very seriously. But then, in October 2020, the analysis was completed and the results were disappointing. BLC1 was almost certainly interference. The signal had appeared multiple times during observations of Proxima Centauri, but it had also appeared during observations of other stars. It was always at roughly the same frequency, always showing the same characteristics. This suggested it wasn't coming from Proxima Centauri specifically. It was coming from somewhere on or near Earth, and it just happened to appear in the data when the telescope was pointed at Proxima Centauri. Further analysis revealed that the signal's frequency drift was too fast to be consistent with a planet. If it was coming from a planet orbiting Proxima Centauri, the drift should have been much slower. The observed drift was more consistent with interference from a moving source on Earth, like a satellite or aircraft passing through the telescope's field of view. The team published their findings in 2 papers in late 2021. BLC1 was not an alien signal. It was interference. But the analysis was thorough and transparent. They explained exactly how they investigated the signal, what tests they performed, and why they concluded it wasn't extraterrestrial. This is how science works. You detect something interesting. You investigate it carefully. You test all the explanations, and sometimes you conclude that it's not what you hoped it was. The BLC1 case illustrates the challenge of SETI. Radio interference is everywhere. Earth is saturated with radio transmissions, cell phone towers, satellites, Wi-Fi networks, radar systems, all producing signals that can leak into radio telescopes and create false positives. Distinguishing between a real alien signal and terrestrial interference requires extremely careful analysis. you need to detect the signal multiple times. You need to verify that it's coming from the same location in space. You need to check that it doesn't match any known sources of interference. And even then, you can't be completely certain unless you decode the signal and extract meaningful information from it. This brings us back to the central question. What would a real alien signal look like? How would we know if we detected one? The most conservative answer is that a real alien signal would be repeatable, verifiable, and decodable. It would appear multiple times, allowing us to study it in detail. It would come from a specific location in space, not from a moving satellite or terrestrial source. And it would contain information, some kind of pattern or structure that couldn't be explained by natural processes. The problem is that most of the signals we've detected don't meet all these criteria. The wow signal appeared once and never repeated. FRBs repeat, but they don't seem to carry information. They're just bursts of energy. BLC1 appeared multiple times, but it turned out to be interference. We haven't yet detected a signal that ticks all the boxes, but that doesn't mean we should stop looking. The universe is vast. There are billions of stars in our galaxy, each one a potential host for planets. Many of those planets could be in the habitable zone. Some of them could have developed life, and some of that life could have developed technology. The question isn't whether intelligent life exists elsewhere, it's whether we can detect it, and whether it wants to be detected. There's a concept in SETI called the Great Silence. If the galaxy is full of intelligent civilizations, why haven't we heard from them? Why haven't we detected their signals? There are many possible answers. Maybe intelligent civilizations are rare. Maybe they exist, but they're too far away for us to detect their signals. Maybe they don't use radio waves for communication. Maybe they do use radio waves, but they only broadcast for a brief period before switching to more advanced technologies. Maybe they're deliberately avoiding contact. Maybe they're listening, just like we are, but nobody's transmitting. Or maybe we have detected their signals, but we didn't recognize them. This last possibility is particularly intriguing. What if FRBs are alien signals, but we've dismissed them as natural phenomena because they don't look like what we expected? What if the wow signal was a deliberate transmission, but it was only broadcast once as a test? What if there are signals in the data we've already collected, but we haven't analyzed them correctly? Radio telescopes generate enormous amounts of data, terabytes per day. Processing all this data requires powerful computers and sophisticated algorithms. And even with modern technology, it's impossible to analyze every signal in detail. Most signals are filtered out automatically, classified as noise or interference. Only the most promising candidates get scrutinized by human researchers. But this filtering process might be throwing away real signals. If an alien civilization uses a modulation technique we're not looking for, their signal might get filtered out before anyone even looks at it. This is why SETI researchers are developing machine learning algorithms to analyze radio telescope data. These algorithms can search for patterns that humans might miss, patterns that don't fit our preconceived notions of what an alien signal should look like. In 2020, researchers at Breakthrough Listen used machine learning to reanalyze old data and discovered dozens of new signal candidates that had been missed in the initial analysis. Most of these turned out to be interference, but the point is that machine learning found them. A human analyst probably wouldn't have. As our algorithms improve, we might find signals that have been hiding in the data all along. There's another category of mysterious signals that deserves mention: periton signals. These were detected by the Parkes radio telescope in Australia between 2015. They were brief bursts of radio waves, similar to FRBs, but they had unusual properties. They appeared at multiple frequencies simultaneously, which is atypical for FRBs. And they seemed to correlate with activity at the telescope facility. For years, astronomers couldn't figure out what was causing them. They checked for satellites, aircraft, lightning, solar flares, all the usual suspects. Nothing matched. Then, in 2015, someone made a connection. The periton signals appeared at lunchtime, always around noon or 1 p.m. This suggested a human cause. Someone at the facility was doing something during lunch that generated radio interference. Further investigation revealed the culprit: microwave ovens. When someone opened the microwave door before the timer finished, while the magnetron was still running, it released a brief burst of radio waves. That burst leaked into the telescope and created a signal that looked like an FRB. This discovery was both amusing and frustrating. Amusing because the mystery had such a mundane explanation. Frustrating because it showed how easily radio telescopes can be fooled by terrestrial interference. If a microwave oven can create a signal that mimics an FRB, what else might be creating false positives? The periton case also highlights an important point. Just because we don't understand a signal doesn't mean it's alien. It might just mean we haven't found the right explanation yet. Science progresses by ruling out possibilities. You detect something strange. You test hypotheses. You eliminate the ones that don't fit. And eventually, you narrow it down to the most likely explanation. Sometimes that explanation is exotic, like pulsars or magnetars. Sometimes it's mundane, like microwave ovens. But you have to do the work. You have to investigate. You can't just assume that an unexplained signal is evidence of aliens. That's not science. That's wishful thinking. So, where does this leave us? We're detecting signals from space that we can't fully explain. FRBs remain mysterious, even after nearly 2 decades of study. The WOW signal is still unexplained after almost 50 years. BLC-1 turned out to be interference. But there will be other candidates. And every year, we're getting better at detecting and analyzing these signals. New telescopes are coming online. The Square Kilometer Array, currently under construction in South Africa and Australia, will be the most sensitive radio telescope ever built. It will detect signals that current telescopes can't see. It will catalog thousands of FRBs. It will search millions of stars for signs of intelligent life. The Chinese 500-meter aperture spherical telescope, known as FAST, is already operational. It's the world's largest single-dish radio telescope. It's conducting SETI observations. It's monitoring pulsars. It's studying FRBs. And it's generating data at an unprecedented rate. These new instruments will either solve the mysteries or deepen them. They'll either explain FRBs conclusively or reveal new types of signals we haven't seen before. They'll either find evidence of extraterrestrial intelligence or confirm that we're alone, at least in our corner of the galaxy. But here's the thing. Even if we never detect an alien signal, even if every mysterious signal turns out to have a natural explanation, the search is still worthwhile, because we're learning. We're discovering new astrophysical phenomena. We're pushing the boundaries of technology. We're developing new techniques for data analysis. And we're forcing ourselves to think carefully about what we expect to find. Every time we investigate a mysterious signal, we learn something about the universe. Pulsars were discovered because someone investigated an anomaly. FRBs were discovered because someone noticed a brief flash in old data. Magnetars were theorized because astronomers couldn't explain certain X-ray bursts. Science advances by investigating anomalies. The things that don't fit. The signals that shouldn't exist. And sometimes, those investigations lead to fundamental discoveries. So, when we talk about mysterious signals from space, we're not just talking about aliens. We're talking about the edge of our knowledge. The place where our understanding of physics meets the unknown. Every unexplained signal is a challenge, a puzzle to be solved, a question to be answered. And the fact that we're asking these questions, that we're building telescopes and analyzing data and searching for answers, that's what makes us human. We're curious. We want to understand. We look up at the sky and wonder what's out there. And sometimes, the sky looks back. Sometimes it sends us signals, brief flashes of radio waves, pulses of energy, patterns in the noise. And we don't always know what they mean, but we keep listening. We keep searching. We keep investigating, because that's what we do. That's who we are. We're the species that looks up at the stars and asks questions. And someday, maybe someday soon, one of those mysterious signals will turn out to be the answer we've been looking for. A message from another world. Proof that we're not alone. Or maybe not. Maybe every signal will have a natural explanation. Maybe the universe is full of strange physics, exotic objects, phenomena we haven't imagined. Maybe we'll spend centuries cataloging mysteries and solving them one by one. But either way, we'll learn, we'll grow, we'll expand our understanding of the cosmos, and we'll do it by investigating the signals we can't explain. Let me tell you about one more mystery. This one is more recent, and it's still developing. In 2022, astronomers detected a signal unlike anything seen before. It was coming from a source designated glimmers XJ 16275.9.5 to 5235004.2, located about 4,000 light-years away, or about 23,500 billion miles. The source emits pulses of radio waves, similar to a pulsar, but here's what makes it strange. It pulses every 18 minutes. That's far too slow for a pulsar. Pulsars spin rapidly, sometimes hundreds of times per second. Even the slowest known pulsars spin once every few seconds. An 18-minute period is completely outside the normal range, but it gets stranger. The pulses are highly polarized, meaning the radio waves oscillate in a specific direction. This is characteristic of emission from a strong magnetic field, and the pulses are incredibly bright. Each pulse releases about as much energy as the sun emits in 20 years, concentrated into a 60-second pulse. Astronomers have proposed that the source might be a magnetar, a neutron star with an ultra-strong magnetic field. But even magnetars don't typically pulse every 18 minutes. The theory is that this magnetar might be spinning very slowly, perhaps because it's old and has lost most of its rotational energy. And its magnetic field might be so strong that it can still generate radio emission even at this slow rotation rate. But this is speculation. We don't have another object like this to compare it to. It's unique. And unique objects are always suspicious in astronomy. When you find something that doesn't fit any category, it's either a new type of object or it's something we don't understand about an existing type. The source has been observed multiple times since its discovery. It keeps pulsing every 18 minutes. It's real. It's not a glitch. It's not interference. It's something out there in space, radiating enormous amounts of energy at a rate that doesn't match any known object, and we don't know what it is. This is the state of the field. We're detecting signals that challenge our understanding. We're cataloging phenomena that don't fit our models. And we're constantly revising our theories to account for new observations. Science is not a collection of facts. It's a process, a way of investigating the world. You observe, you hypothesize, you test, you revise, and sometimes you discover something completely unexpected. Something that forces you to rethink everything you thought you knew. The mysterious signals we're detecting might be harbingers of such a discovery. They might be telling us that our understanding of neutron stars is incomplete, or that there are exotic forms of matter we haven't theorized yet, or that the universe can produce phenomena we haven't imagined, or, just maybe, that we're not alone. That somewhere out there, another civilization is broadcasting, sending signals into the void, hoping that someone, somewhere, is listening. And we are listening. We've been listening for over 60 years now. Ever since Frank Drake conducted the first modern SETI experiment, Project Ozma, in 1960, he pointed a radio telescope at two nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for signals. He didn't find anything. But he established a methodology, a scientific approach to searching for extraterrestrial intelligence. Since then, SETI has grown. We have dedicated facilities. We have international collaborations. We have algorithms that can process billions of signals per second. We're listening to thousands of stars. We're monitoring the sky continuously. We're analyzing data from multiple telescopes, and we're getting better at it every year. But we still haven't found a confirmed alien signal. We've found plenty of interesting signals, plenty of mysteries, but nothing that definitively says, we are here. This is sometimes called the Fermi paradox, named after physicist Enrico Fermi. If intelligent life is common in the galaxy, if there are millions or billions of civilizations out there, why haven't we heard from them? Where is everybody? There are many proposed solutions to the Fermi paradox. Maybe intelligent life is rare. Maybe civilizations destroy themselves before they develop interstellar communication. Maybe they're deliberately hiding. Maybe they exist, but they're so different from us that we don't recognize their signals. Maybe the galaxy is teeming with life, but everyone's listening and nobody's transmitting. Maybe interstellar communication is harder than we think. Maybe signals degrade over interstellar distances in ways we don't understand. Maybe advanced civilizations don't use radio waves at all. Or maybe we're just early. Maybe intelligent life is common, but it takes billions of years to develop, and we're among the first. The vanguard of consciousness in a young universe. We don't know, and that uncertainty is both frustrating and exciting. Frustrating because we want answers. We want to know if we're alone. Exciting because the question is still open. The search continues, and every day we're generating new data, new signals, new mysteries. Some of them will be solved. Some will remain mysterious for decades. And some, just maybe, will turn out to be the discovery of a lifetime. First contact. But until then, we keep listening. We keep investigating. We keep searching for explanations. We keep pushing the boundaries of what's known, because that's what we do. That's what it means to be human, to wonder, to question, to seek understanding, even when the answers are elusive, even when the signals are mysterious, even when the universe keeps its secrets. Let's talk about the implications. If we did detect a confirmed alien signal, what would happen? The first step would be verification. We'd need to confirm that the signal is real, that it's not interference, that it's actually coming from space. This would require multiple telescopes observing the same source independently. We'd need to rule out all natural explanations. We'd need to analyze the signal's properties in detail, and we'd need to be absolutely certain before making any public announcement, because a false alarm would damage the credibility of SETI research. It would undermine public trust in science, and it would make future detections harder to take seriously. So the bar for claiming detection of an alien signal is extremely high. It has to be. But let's say we do detect a confirmed signal. What then? The International Protocol for Announcing the Detection of Extraterrestrial Intelligence, established by the SETI community, outlines the steps. First, inform other scientists. Give them a chance to verify the detection independently. Second, inform relevant government authorities. Third, inform the public. Be transparent about what was detected and how. And fourth, do not respond. Do not send any message back. Not without international consensus. This last point is crucial. If we detect an alien signal, humanity needs to decide collectively how to respond. It's not a decision for one person, one country, or one organization. It's a decision for the species. And it's a decision with profound consequences. Responding to an alien signal could be the most important act in human history. Or it could be a catastrophic mistake. We don't know. We don't know who's sending the signal. We don't know their intentions. We don't know how they'll interpret our response. We don't even know if they're still alive. The signal we detect might be thousands or millions of years old. The civilization that sent it might be long gone. We could be listening to a message from the past. A fossil signal from a dead civilization. This is the sobering reality of interstellar communication. The distances are so vast. The timescales are so long that any conversation would span generations, maybe millennia. You send a message. Your descendants, many generations later, might receive a reply, and their descendants might send the next message. It's not a conversation in any normal sense. It's more like leaving notes for the future. But even that would be extraordinary. It would confirm that we're not alone. It would tell us that intelligence can survive and thrive, that civilizations can endure for thousands or millions of years, that the universe is, in some sense, alive, aware, capable of understanding itself. And that would change everything. Our philosophy, our religion, our sense of purpose. All of it would be transformed by the knowledge that we share the universe with other minds, other civilizations, other perspectives on existence. But we're not there yet. We haven't detected a confirmed alien signal. We've detected mysteries, anomalies, signals we can't explain, and that's where we are, on the edge of discovery, listening, waiting, wondering, and the signals keep coming. FRBs flash across the sky every day. Pulsars tick like cosmic clocks. Strange sources like Gleam X pulse slowly in the darkness. And somewhere in all that data, in all those signals, there might be an answer, a message, a sign that we're not alone, or maybe not. Maybe the universe is stranger than we imagine. Maybe the signals we're detecting are natural phenomena we haven't understood yet. Maybe we're decades or centuries away from solving these mysteries. But that's okay, because the search itself is meaningful. The questions we're asking are important. And the tools we're developing, the telescopes, the algorithms, the international collaborations, they're expanding our understanding of the cosmos. Whether we find aliens or not, we're learning, we're discovering, we're exploring the universe in ways that previous generations could only dream of. And that's something to celebrate. So when you look up at the night sky, remember this: the stars you see are transmitting. They're sending signals across vast distances. Radio waves, light, gravitational waves. The universe is full of signals. Most of them are natural. The hum of gas clouds, the tick of pulsars, the flash of verbs. But some of them, maybe just a few, might be something more. Messages from other worlds. Signals from civilizations we've never met. Voices calling across the void. And we're listening. We're out here, on this small planet, orbiting an ordinary star in an unremarkable part of the galaxy. And we're listening, searching for a signal, a sign, proof that we're not alone. And maybe, someday, we'll find it. Or maybe the silence will continue. Maybe we'll keep detecting mysteries, keep cataloging anomalies, keep wondering what it all means. But either way, we'll keep looking, we'll keep listening, we'll keep asking questions, because that's what we do. We're the species that looks up at the stars and wonders, the species that builds telescopes and searches for answers, the species that refuses to accept that the universe is silent. And as long as we keep listening, there's hope. Hope that we'll detect something. Hope that we'll understand. Hope that one day, one of those mysterious signals will turn out to be the answer we've been searching for. A message from the stars. Proof that we're not alone in the cosmos. That somewhere out there, someone else is looking up at their sky, wondering the same things, asking the same questions, listening for a signal from us. And maybe, just maybe, we'll find each other. Across the vast emptiness of space, across the enormous gulfs of time, we'll make contact. We'll exchange information. We'll learn about each other. And the universe will become a little less lonely, a little less silent, a little more alive. But until then, we wait, we listen, we investigate every mysterious signal, we analyze every anomaly, we follow every lead. Because somewhere, in all that noise, in all that static, in all those mysterious bursts and pulses and signals we can't explain, there might be something real, something profound, something that changes everything, and we won't know unless we look. So we keep looking, we keep listening, we keep searching, and the universe keeps sending signals, mysterious signals, signals we can't explain, not yet. But someday, maybe someday soon, we'll understand. We'll decode the message. We'll solve the mystery. And we'll discover that the universe has been trying to tell us something all along. We just had to learn how to listen. Thank you for joining me on this journey through the mysterious signals from space. If you found this exploration compelling, please consider liking this video and subscribing to the channel. Your support helps me continue investigating these deep mysteries of the cosmos. And remember, right now, as you're hearing these words, radio telescopes around the world are listening, monitoring the sky, detecting signals, some of them natural, some of them mysterious, and maybe, just maybe, some of them from somewhere or someone far beyond our world. But there's another dimension to this mystery that we need to explore: the technology itself. How do we actually listen to these signals? What does a radio telescope do? How do we distinguish between a real signal and interference? Understanding this helps us appreciate just how challenging this search really is. A radio telescope is fundamentally different from an optical telescope. An optical telescope collects visible light using mirrors or lenses. It focuses that light to create an image. A radio telescope collects radio waves using a large dish, similar to a satellite dish, but much bigger. The dish reflects radio waves to a receiver at the focal point. The receiver converts the radio waves into electrical signals, and those signals get amplified and recorded for analysis. The larger the dish, the more sensitive the telescope. The Arecibo telescope in Puerto Rico, before it collapsed in 2020, had a dish 305 meters across. That's 1,000 feet. It was one of the most sensitive radio telescopes in the world. The FAST telescope in China is even larger, 500 meters across. That's 1,640 feet. But even these giant dishes can't see everything. Radio waves come in different frequencies, measured in hertz. A hertz is one wave cycle per second. Radio waves range from about 10 kilohertz to 300 gigahertz. That's 10,000 cycles per second, up to 300 billion cycles per second. Each telescope is designed to observe a specific range of frequencies. The receiver electronics are tuned to amplify certain frequencies and filter out others. This is necessary because the sky is full of radio noise. Lightning produces radio waves. The sun produces radio waves. Jupiter produces extraordinarily powerful radio emissions. And Earth is saturated with human-made radio signals. Cell phone towers, Wi-Fi networks, GPS satellites, radar systems, microwave ovens, car ignition systems, fluorescent lights. All of these produce radio waves that can interfere with astronomical observations. Distinguishing between an astronomical signal and terrestrial interference is one of the biggest challenges in radio astronomy. This is why many radio telescopes are located in remote areas. The Parkes telescope is in rural Australia, far from major cities. The Greenbank telescope in West Virginia is located in the National Radio Quiet Zone, where radio transmissions are strictly limited to protect the telescope from interference. The VLA, the Very Large Array in New Mexico, is in a desert valley surrounded by mountains that block radio signals from distant cities. But even with these precautions, interference is everywhere. Satellites pass overhead constantly. Aircraft flying at high altitude can reflect ground-based signals into the telescope. Even cosmic rays hitting the receiver electronics can create spurious signals. So, astronomers use multiple techniques to filter out interference. One technique is to observe the same source with multiple telescopes simultaneously. If a signal appears in data from multiple telescopes at the same time, it's probably real. If it appears in only one telescope, it's probably interference. Another technique is to rapidly switch the telescope between the target source and a nearby patch of empty sky. If the signal appears when pointed at the source, but disappears when pointed away, it's probably coming from that source. If the signal appears constantly, Regardless of where the telescope is pointed, it's probably interference from Earth or a satellite. A third technique is to analyze the signal's frequency drift. Astronomical sources are moving relative to Earth due to the rotation of the planet, the orbit around the Sun, and the motion of the source itself through space. This motion causes a Doppler shift in the frequency, just like how a police siren sounds higher-pitched when approaching and lower-pitched when receding. A real astronomical signal should show a smooth, predictable drift in frequency over time. Terrestrial interference typically doesn't show this drift, or it shows erratic jumps as satellites move or aircraft change course. These techniques are powerful, but they're not perfect. Some interference can mimic an astronomical signal very convincingly, and some astronomical signals might have properties that make them look like interference. This is why the search for extraterrestrial intelligence requires extraordinary caution. A single detection, no matter how compelling, isn't enough. You need multiple detections, confirmation from independent telescopes, detailed analysis of all the signal's properties. And even then, you have to be prepared for the possibility that it's something mundane. Let's talk about another category of mysterious signals: radio transients from the galactic center. The center of our galaxy is a chaotic place. There's a supermassive black hole there, Sagittarius A, with a mass of about 4 million suns. There are dense clusters of stars orbiting close to the black hole. There are clouds of gas and dust being heated to millions of degrees. And there's a lot of radio emission. Most of this emission is steady or slowly varying. But occasionally, astronomers detect brief radio transients from the galactic center, signals that flare up suddenly, last for a few hours or days, and then disappear. These transients don't fit the profile of known sources. They're not pulsars, which pulse regularly. They're not FRBs, which last only milliseconds. They're not supernova remnants, which glow steadily for years. They're something else. One hypothesis is that they're caused by stars passing close to Sagittarius A. When a star gets too close to a black hole, it can be torn apart by tidal forces. This creates a brief flare of radiation as the star's material falls into the black hole. But the observed transients don't quite match this model. They don't have the right spectrum, the distribution of energy across different wavelengths, and they don't last long enough. Another hypothesis is that they're caused by magnetic activity on stars near the galactic center. Some stars have extremely strong magnetic fields. When these fields reconnect and release energy, they can produce powerful flares. But again, the observed transients don't quite match. They're brighter than expected and have unusual properties. So we have another mystery: regular radio transients from the galactic center that don't fit any known source category. They might be a new type of stellar flare. They might be related to the black hole's activity, or they might be something we haven't thought of yet. The data is limited because the galactic center is a difficult region to observe. It's obscured by dust, invisible light. It's crowded with sources in radio wavelengths. And it's 26,000 light-years away, or about 153 trillion miles, which means the signals we detect today were emitted 26,000 years ago. But as telescopes improve, we're collecting more data. We're detecting more transients. And slowly, we're building up a picture of what's happening in that chaotic region. Let me tell you about the Arecibo message. In 1974, to mark the remodeling of the Arecibo radio telescope, astronomers decided to broadcast a message into space. The target was M13, a globular cluster containing about 300,000 stars, located about 25,000 light-years away, or about 147 trillion miles. The message was designed by Frank Drake and Carl Sagan. It contained 1,679 binary digits, ones and zeros. These digits were arranged in a pattern that, when displayed as a grid, created a pictogram. The pictogram showed the numbers 1 through 10 in binary, the atomic numbers of hydrogen, carbon, nitrogen, oxygen, and phosphorus, the elements that make up DNA, the formulas for the sugars and bases in DNA, the structure of DNA itself, a figure of a human, the height of an average human, the population of Earth, a diagram of our solar system showing Earth's position, and a diagram of the Arecibo telescope itself. The entire message was transmitted in less than 3 minutes. It was broadcast at a frequency of 2,380 MHz with a power of about 450 kilowatts. This made it, briefly, the brightest object in the radio sky at that frequency. If there are any civilizations in M13 with radio telescopes, they'll receive the message in about 25,000 years. And if they reply, we'll get their response in about 50,000 years. So don't hold your breath. The Arecibo message wasn't really a serious attempt to contact aliens. It was more of a demonstration. A proof that we could broadcast a signal powerful enough to be detected across interstellar distances. But it raised interesting questions. What should we say to aliens? How do we encode information in a way that's universally understandable? Do we have the right to speak for all of humanity? These questions are at the heart of METI, messaging to extraterrestrial intelligence. METI is different from SETI. SETI listens passively. METI broadcasts actively. And METI is controversial. Some scientists argue that broadcasting our location to the galaxy is dangerous. We don't know who's listening. We don't know their intentions. If there's a hostile civilization out there, broadcasting might be like lighting a campfire in a forest full of predators. You might attract attention you don't want. Others argue that advanced civilizations probably aren't hostile. Any species that survives long enough to develop interstellar communication has probably learned to cooperate, to manage resources, to avoid self-destruction. Hostile civilizations destroy themselves before they become spacefaring. And besides, if there are advanced aliens scanning the galaxy for signs of life, they've probably already detected us. We've been leaking radio and television signals into space since the 1920s. Those signals have spread outward in an expanding sphere, now over 100 light-years in radius. Any civilization within that sphere with sufficiently sensitive telescopes could detect our broadcasts. They already know we're here. So broadcasting a deliberate message might not make much difference. These are unresolved debates. There's no international consensus on whether we should broadcast to aliens. Some organizations, like METI International, conduct broadcasts occasionally. Others, like many members of the SETI community, think we should listen only until we understand the situation better. But the Arecibo message was just the beginning. Since 1974, several other messages have been broadcast. In 2008, Doritos sponsored a transmission of an advertisement toward a solar system 42 light-years away. In 2017, a message containing music, math, and science tutorials was broadcast toward GJ273, a red dwarf star 12 light-years away. These broadcasts are symbolic gestures more than serious attempts at communication. But they raise the question, if we did want to communicate with aliens, how would we do it? Language is a problem. Any human language assumes shared concepts, shared experiences, shared biology. An alien species might not have vision, so concepts like color might be meaningless to them. They might not have hearing, so music might be incomprehensible. They might not have a concept of individuality, so the idea of a single person might not make sense. So, we need a universal language, something based on mathematics and physics, concepts that should be the same everywhere in the universe. The number pi is the same on Earth and on a planet orbiting a distant star. The speed of light is the same everywhere. The structure of the hydrogen atom is the same everywhere. These are universal constants. If we base our message on these constants, we have a better chance of being understood. This is the approach taken by most serious METI proposals. Use prime numbers to establish that the message is artificial. Use binary code to transmit information efficiently. Use pictograms based on fundamental physics and chemistry to convey complex ideas. But even with these techniques, communication is incredibly challenging. Imagine trying to explain the concept of democracy to someone who has never experienced a society, or trying to explain what music sounds like to someone who has never heard sound. That's the level of difficulty we're facing when trying to communicate with an alien intelligence. They might be so different from us that finding common ground is nearly impossible. But that doesn't mean we shouldn't try, because even a failed attempt at communication teaches us something. It forces us to think about what's truly universal. What concepts transcend species, planets, and biology. And it reminds us that we're part of something larger, part of a cosmos that might be full of minds, perspectives, and experiences vastly different from our own. Let's return to the mystery of FRBs and dig deeper. One of the most intriguing aspects of FRBs is their dispersion measure. This is the amount of delay between high and low frequency radio waves as they travel through space. When radio waves pass through ionized gas, plasma, the lower frequencies are slowed down more than the higher frequencies. By measuring this delay, astronomers can calculate how much plasma the signal passed through, and from that, they can estimate the distance to the source. Most FRBs have very high dispersion measures. This indicates they've traveled through a lot of plasma, more plasma than exists in our galaxy alone. This tells us that most FRBs are extragalactic. They're coming from other galaxies. But here's where it gets interesting. The amount of plasma between galaxies, the intergalactic medium, is not well known. It's very diffuse, very hard to detect directly. FRBs might be a new way to study the intergalactic medium. By detecting FRBs from different distances and measuring their dispersion, we can map how much plasma exists between here and there. This gives us information about the structure of the universe on large scales. It tells us about the distribution of matter in intergalactic space, and it helps us understand how galaxies are connected by filaments of gas and dark matter. Several research groups are using FRBs as cosmological probes. They're trying to constrain the amount of baryonic matter, ordinary matter, made of protons and neutrons, in the universe. Theory predicts a certain amount of baryonic matter based on models of the Big Bang. But when we add up all the stars, gas clouds, and galaxies we can see, we come up short. About half the baryonic matter is missing. It's somewhere, but we can't see it directly. One hypothesis is that it's in the intergalactic medium, diffuse, ionized gas spread throughout space, too thin to glow brightly enough to detect with conventional telescopes. FRBs might be able to detect this missing matter through the dispersion of their signals. If FRB signals are traveling through this diffuse plasma, they'll be dispersed. And by measuring that dispersion across many FRBs, we can estimate the total amount of plasma and therefore the total amount of missing baryonic matter. This is called the baryon census, and it's one of the major unsolved problems in cosmology. FRBs might help solve it. But only if we understand what FRBs are and where they're coming from. And that brings us back to the central mystery. What produces an FRB? The leading model is magnetars. These are neutron stars with magnetic fields of 10 to the 15th Gauss. That's 1,000 trillion times stronger than Earth's magnetic field. These fields are so intense that they warp the structure of the neutron star itself. They can crack the crust, cause starquakes, and release enormous amounts of energy. When a magnetar flares, it can release as much energy in a fraction of a second as the sun releases in 100,000 years. Most of this energy is released as X-rays and gamma rays, but some might be released as radio waves. If the flare is powerful enough and the conditions are right, it might produce a burst of coherent radio emission. This radio burst would be brief, lasting only milliseconds. It would be extraordinarily bright, and it would be detectable across millions or billions of light years. This is the magnetar model for FRBs, and it has some support. In April 2020, astronomers detected an FRB from within our own galaxy, FRB 200428. It came from SGR 1935 plus 2154, a known magnetar located about 30,000 light-years away, or about 176 trillion miles. The FRB was detected simultaneously by multiple radio telescopes around the world. And at the exact same time, X-ray and gamma-ray telescopes detected a flare from the same magnetar. This was the smoking gun. Direct evidence that magnetars can produce FRBs. It was the first time an FRB had been definitively associated with a known source. But here's the thing. FRB 200428 was much weaker than most FRBs. If it had been located in another galaxy, we probably wouldn't have detected it. The FRBs we detect from extragalactic sources are thousands or millions of times more energetic. So, either those FRBs are coming from extraordinarily powerful magnetars, much more powerful than SGR 1935 plus 2154, or there's something else going on. Some additional mechanism that amplifies the signal. One possibility is that the radio waves are being focused, beamed in a specific direction. If the magnetar's magnetic field channels the emission into a narrow beam, and Earth happens to be in the path of that beam, we'd see a much brighter signal than if the emission were isotropic, spread equally in all directions. This is similar to how a lighthouse works. The light from a lighthouse isn't actually that bright, but it's focused into a beam by mirrors and lenses. If you're in the path of the beam, you see a very bright flash. If you're off to the side, you see nothing. Magnetar flares might work the same way. The magnetic field might act like a lens, focusing radio waves into a beam, and we only detect the FRB if we're in the beam's path. This would explain why FRBs seem so bright. It would also explain why they're rare. Most magnetar flares would be beamed away from us, so we wouldn't see them. We'd only detect the ones that happen to be pointed in our direction. But this is still speculation. We don't fully understand how magnetic fields work. We don't know exactly how they produce radio emission. We don't know if beaming is possible or common. So, the mystery remains. FRBs are probably produced by magnetars, but the details are still unclear. And there might be multiple mechanisms, different types of magnetar activity producing different types of FRBs. let me tell you about another class of mysterious signals. Odd radio circles, or AURs. These were discovered in 2019 by a team using the Australian Square Kilometer Array pathfinder, ASCAP. They were analyzing data from a radio survey of the sky when they noticed something strange. Circular structures in the radio images. Perfect circles, or nearly perfect circles. Each one about 1 million light-years across, or about 5.8 trillion miles. These aren't objects in our galaxy. They're associated with distant galaxies, billions of light-years away. When astronomers look at the centers of these circles, they often find a galaxy, but the circle itself is much larger than the galaxy. It's a vast ring of radio emissions surrounding the galaxy, and nobody knows what causes it. The circles are too large to be supernova remnants. They're too symmetrical to be random structures. They don't match the profile of any known type of galaxy or cosmic structure. One hypothesis is that they're related to shock waves from galactic activity. Maybe a supermassive black hole at the center of the galaxy underwent a period of intense activity, blowing out jets of material. Those jets would push through the surrounding gas, creating a shock wave, and that shock wave, over millions of years, would expand into a giant spherical shell. If we're seeing that shell edge on, it would look like a circle in radio images. This is plausible, but it's not proven. Another hypothesis is that they're related to mergers of supermassive black holes. When two galaxies merge, their central black holes eventually merge too. This merger releases an enormous amount of energy in the form of gravitational waves. It might also trigger a burst of activity that creates a shock wave. Or maybe AURs are something entirely new, a phenomenon we haven't predicted, an aspect of galaxy evolution we don't understand. This is what makes them so intriguing. They don't fit any existing model. They challenge our understanding of what galaxies can do, and as we detect more of them, we might discover patterns that lead to an explanation, or we might find that they're even stranger than we thought. There's a philosophical dimension to all of this. The mysterious signals we're detecting, the phenomena we can't explain, they remind us of something important. Our knowledge is limited. Our understanding of the universe is incomplete. We've made enormous progress. We've discovered pulsars, black holes, gravitational waves, the expansion of the universe. We've mapped the cosmic microwave background. We've detected planets around other stars. We've photographed the event horizon of a black hole. These are extraordinary achievements. But the universe keeps surprising us. It keeps presenting phenomena that don't fit our theories. FRBs, AURs, anomalous signals from the galactic center, transients that appear and disappear. Every time we build a better telescope, we find something new, something we didn't predict, something that challenges our understanding. And this is how science progresses. Not by confirming what we already know, but by discovering what we don't know, by finding anomalies, by investigating mysteries, by being willing to say, I don't understand this yet. The mysterious signals from space are important, not because they might be aliens, though that would be extraordinary. They're important because they push us. They force us to think harder, to develop better theories, to build better instruments, to collaborate across borders and disciplines. Every mysterious signal is an opportunity to learn something new about the universe, and an opportunity to realize how much we still have to learn. The universe is vast. It's been around for 13.8 billion years. It contains trillions of galaxies, each with billions of stars, many with planets. The conditions for life as we know it exist on countless worlds. And yet, we've only been listening to the cosmos for about 60 years. That's less than a human lifetime. It's a blink of an eye on cosmic timescales. So when we ask, where is everybody? Why haven't we detected aliens? We should remember that we've barely started looking. We've surveyed a tiny fraction of the sky. We've listened to a tiny fraction of the radio spectrum. We've analyzed a tiny fraction of the data we've collected. And we've only been doing this for a few decades. If intelligent civilizations are rare, if they exist but are quiet, if they're using communication methods we haven't thought of, we might not detect them for centuries or millennia. Or we might detect them tomorrow. Let's explore what happens when we detect a signal. The practical side of analysis. When a radio telescope detects something unusual, it triggers a cascade of investigation. The data is flagged by automated software. An astronomer reviews it. If it looks interesting, they schedule follow-up observations. This is where most signals die. Follow-up observations with the same telescope show nothing. The signal was a glitch, a satellite, a piece of interference. It's gone. But occasionally, very occasionally, the signal persists. It appears again in the follow-up data. It's coming from the same location in the sky. It has the same properties. This is when things get interesting. The astronomer contacts colleagues. They request observations from other telescopes. This is crucial. Independent confirmation from a different telescope, at a different location, using different equipment, eliminates most sources of error. If multiple telescopes detect the same signal, it's almost certainly real. Then comes the detailed analysis. What frequency is the signal at? Is it narrowband or broadband? Is it polarized? Does it show any modulation, any pattern in how the intensity varies over time? Does it repeat? If so, is the repetition periodic or random? All of these properties provide clues about what's producing the signal. Let's imagine a scenario. Suppose a telescope detects a narrowband signal at 1420 MHz. That's the hydrogen line, the same frequency as the wow signal. The signal lasts for several minutes. It shows a slight drift in frequency, consistent with a source that's accelerating relative to Earth. Follow-up observations confirm it. The signal appears every time the telescope points at a specific star system. It doesn't appear when pointed elsewhere. Multiple telescopes in different countries detect it independently. This is an extraordinary situation. Everything about the signal suggests it's real. It's coming from space. It's associated with a specific star. It's at a frequency that would make sense for interstellar communication. What happens next? First, the team would analyze the signal in extreme detail. They'd record it at high time resolution, capturing every millisecond. They'd examine the frequency spectrum with high precision, looking for any fine structure or modulation. They'd check for polarization, whether the radio waves are oscillating in a specific direction. They'd look for patterns in the signal, repeating sequences, anything that might indicate information content. If the signal is modulated, if it carries information, this is where it would become apparent. A simple on-off pattern might be a series of pulses. A more complex modulation might encode data, like how a modem encodes computer data onto audio tones. Decoding an alien signal would be extraordinarily difficult. We wouldn't know the encoding scheme. We wouldn't know what information is being transmitted. We wouldn't even know if it's information in a sense we'd recognize. It might be a beacon, a simple repeating pattern designed to attract attention. It might be a message, an attempt to communicate specific information. It might be unintentional leakage, the alien equivalent of our radio and television broadcasts. Or it might be something we can't comprehend, like a conversation between artificial intelligences using concepts and languages beyond our understanding. But we'd try. Mathematicians would look for patterns. Cryptographers would apply decoding techniques. Computer scientists would use machine learning to search for structure in the data. And all of this would happen under intense scrutiny, because the stakes are enormous. If we announce that we've detected an alien signal and we're wrong, it damages the credibility of the entire field. It undermines public trust in science. It turns SETI into a joke. So the standard of evidence has to be extraordinarily high. The signal has to be confirmed beyond any reasonable doubt. Every alternative explanation has to be ruled out, and the analysis has to be transparent, published, peer-reviewed. Only then would an announcement be made. And that announcement would change the world. Imagine the news breaking. Scientists have detected a signal from another star. The signal is artificial. It's evidence of extraterrestrial intelligence. The reaction would be complex. Some people would be excited, thrilled by the confirmation that we're not alone. Some would be frightened, worried about what contact with aliens might mean. Some would be skeptical, demanding more proof, questioning the evidence. And some would see it through a religious or philosophical lens, interpreting it as confirmation or challenge to their beliefs. Governments would react. They'd want to know what the signal says. They'd want to know if it's a threat. They'd want to control the narrative. There would be calls for secrecy, for withholding information from the public. And there would be calls for transparency, for sharing everything openly. The scientific community has protocols for this. The post-detection protocols, established by the International Academy of Astronautics, outline how to handle a confirmed detection, verify the signal, inform other observatories, inform national authorities, inform the Secretary-General of the United Nations, inform the public. Do not respond without international consensus. These protocols exist because the decision of how to respond is too important for any one person or country to make alone. It's a decision for humanity. But would the protocols be followed? In the moment, with the pressure of the most important discovery in human history, would scientists and governments stick to the plan? Or would there be leaks, competing announcements, national rivalries? We don't know. We've never been in this situation. And hopefully, if it ever happens, cooler heads prevail. But let's step back from this hypothetical and return to reality. The reality is that we haven't detected a confirmed alien signal. We've detected mysteries. Signals that don't fit our models. Phenomena that challenge our understanding. But nothing that definitively says, we are here. And that's okay, because the search itself is valuable. It's teaching us about the universe. It's improving our technology. It's forcing us to think carefully about what we expect to find and why. Let's talk about the Drake equation. This is a framework for thinking about the question of intelligent life in the galaxy. It was proposed by Frank Drake in 1961. The equation is simple. N equals air star times Fp times Ne times Fl times Fe times Fc times Fc times L. Let me break that down. N is the number of civilizations in our galaxy that we might be able to communicate with. R star is the rate at which stars form in our galaxy, about 7 stars per year. Fp is the fraction of those stars that have planets. We now know this is close to 1. Almost every star has planets. NE is the number of planets per star that could support life. The habitable zone planets. Current estimates suggest this is around 0.1 to 0.5. Maybe 1 in every 5 to 10 stars has a potentially habitable planet. FL is the fraction of those planets where life actually develops. This is completely unknown. It might be close to 1 if life emerges easily wherever conditions are right. Or it might be very small if the origin of life requires extraordinarily unlikely chemical reactions. FI is the fraction of life-bearing planets where intelligence evolves. Again, unknown. On Earth, it took billions of years for intelligence to evolve. Is that typical, or are we unusual? FC is the fraction of intelligent species that develop technology capable of interstellar communication. We did it, obviously, but maybe most intelligent species don't. Maybe they lack the resources, the environment, or the motivation. And L is the lifetime of a technological civilization. How long, on average, does a civilization survive after developing radio technology? This is perhaps the most important and most uncertain parameter. If civilizations typically destroy themselves within 100 years of developing technology through nuclear war, climate change, or other catastrophes, then L is small, and there would be very few civilizations in the galaxy at any given time. If civilizations typically survive for millions of years, becoming stable, sustainable, and spreading through their stellar neighborhood, then L is large, and the galaxy could be teeming with civilizations. We don't know. We have exactly one data point, us, and we've only been technological for about 100 years. We don't even know our own L yet. Different assumptions about these parameters lead to wildly different estimates for N. Optimistic assumptions. Life is common. Intelligence is common. Civilizations last a long time. Give N in the millions. The galaxy is full of civilizations. Pessimistic assumptions. Life is rare. Intelligence is rare. Civilizations are short-lived. Give N close to 1. We might be alone in the galaxy. The truth is probably somewhere in between. But until we have more data, until we either detect another civilization or survey enough stars to place statistical limits, we're working with guesses. Educated guesses, informed by what we know about biology, evolution, and astronomy. But still, guesses. The Drake equation isn't meant to give a definitive answer. It's meant to frame the question, to identify what we need to know, to guide our search. If we want to estimate N accurately, we need to measure these parameters. We need to understand how often life emerges on habitable planets. We need to understand how often intelligence evolves. We need to understand how long civilizations last. And the only way to measure these things is to look, to search for biosignatures on exoplanets, to search for technosignatures, signs of technology, in radio emissions and other wavelengths, to study our own civilization and our own risks of self-destruction. This is the work that's ongoing. Astronomers are characterizing exoplanet atmospheres, looking for gases that might indicate life. SETI researchers are scanning the skies, listening for signals. Sociologists and historians are studying the longevity of civilizations, looking for patterns in how societies survive or fail. All of this feeds into our understanding of N. And even if we never detect an alien civilization, this research is valuable. It tells us about our place in the cosmos. It tells us whether we're common or rare. and it tells us what we need to do to survive. Let me tell you about biosignatures. These are different from technosignatures. Biosignatures are signs of life, not necessarily intelligent life. They're gases in a planet's atmosphere that are produced by living organisms. On Earth, the most obvious biosignature is oxygen. Our atmosphere is 21% oxygen. That oxygen is produced almost entirely by photosynthesis, by plants and algae and cyanobacteria. Without life constantly replenishing it, oxygen would react with rocks and disappear from the atmosphere in a few million years. So if we detect oxygen in another planet's atmosphere, it's a strong hint that life is present. There are other biosignatures too. Methane is produced by certain microorganisms. Phosphine might be produced by microbial life. Certain organic molecules, if detected in large quantities, could indicate biological activity. Detecting these gases requires powerful telescopes. The James Webb Space Telescope, launched in 2021, is capable of analyzing the atmospheres of some exoplanets. It uses spectroscopy, splitting light into its component wavelengths to identify which gases are present. When a planet passes in front of its star, from our perspective, some of the star's light passes through the planet's atmosphere. Different gases absorb light at different wavelengths. By measuring which wavelengths are absorbed, we can determine which gases are present. This technique has already been used to detect water vapor, carbon dioxide, and methane in the atmospheres of several exoplanets. But detecting biosignatures is harder. The signals are weak. The planets are small and distant. And there are false positives, non-biological processes that can produce the same gases. For example, oxygen can be produced by the photodissociation of water, where ultraviolet light from the star breaks water molecules apart. Methane can be produced by volcanic activity. Phosphine can be produced by lightning. So, detecting these gases isn't proof of life. It's a hint. A clue that warrants further investigation. If we detect oxygen and methane together, that's more suggestive. These gases react with each other, so they shouldn't coexist in an atmosphere unless something is constantly replenishing them. On Earth, that something is life. Photosynthesis produces oxygen. Bacteria in wetlands produce methane. The two gases are in a constant chemical war, but life keeps both of them present. If we see the same pattern on another planet, it would be strong evidence for life. But it wouldn't be proof. We'd need more observations. We'd need to study the planet over time, looking for seasonal variations that might indicate biological cycles. We'd need to search for other biosignatures, other gases or molecules that strengthen the case. And even then, we might not be certain. Certainty requires either direct imaging, actually photographing the planet and seeing continents and oceans and possibly vegetation, or it requires detection of an unambiguous biosignature, something that absolutely cannot be produced without life. And we don't know if such a signature exists. This is the state of astrobiology today. We have the tools to search for life on other worlds. We have telescopes powerful enough to analyze exoplanet atmospheres. We have theories about what biosignatures to look for, but we haven't found anything yet. We've characterized the atmospheres of dozens of exoplanets. Some have water vapor, some have complex chemistry, but none have shown clear signs of life. Not yet. Maybe life is rarer than we think. Maybe it's there, but we haven't looked at the right planets yet. Or maybe life exists, but it doesn't produce biosignatures we can detect. Maybe alien life uses completely different biochemistry. Maybe it doesn't photosynthesize. Maybe it doesn't produce oxygen or methane. Maybe it's so alien that we wouldn't recognize its signatures even if we saw them. This is the challenge. We're looking for life as we know it. Carbon-based, water-dependent, producing gases and molecules we're familiar with. But life might be more diverse than that. It might use silicon instead of carbon. It might use ammonia instead of water. It might exist at temperatures or pressures we'd consider impossible. And if that's the case, we might be looking in the wrong places with the wrong tools. But we have to start somewhere, and starting with life as we know it is the most logical approach. Because it's the only kind of life we understand. Science is unpredictable. Now, let me talk about something that doesn't get discussed enough: the psychological impact of these mysterious signals, on the scientists who study them, on the public who hears about them, on society as a whole. When Jocelyn Bell detected the first pulsar signals, she experienced genuine anxiety. What if it was an alien signal? What would that mean for her career, for humanity, for everything? The responsibility of possibly being the first human to make contact with another civilization is overwhelming. It's not just about scientific discovery. It's about changing the course of human history. Every scientist working in SETI lives with this possibility. Every time they detect something unusual, there's a moment of adrenaline, a moment of, "Is this it?" And then the careful work begins. The analysis, the checking, the verification, and 99.99% of the time, it's not aliens. It's something mundane, a glitch, interference, a natural phenomenon. But that 0.01% possibility never goes away. Because we know, intellectually, that somewhere in all that data, there might be a real signal. And missing it because we weren't careful enough, because we dismissed it too quickly, would be a tragedy. So, scientists err on the side of caution. They investigate thoroughly. They take mysterious signals seriously, even when they expect them to be nothing. This creates a tension between the excitement of discovery and the weight of responsibility, between hope and skepticism, between wanting to find something and knowing that finding something would be world-changing and potentially dangerous. Now think about the public reaction to these stories. When news breaks about a mysterious signal, social media explodes. People get excited. They speculate. They create theories. Some reasonable, some not so much. And then, when the signal turns out to be natural or interference, there's disappointment. Sometimes, anger. People feel like they were misled. Like scientists, cried wolf. But this misunderstands how science works. Scientists report what they observe. They investigate. They publish their findings. If those findings are, "We detected something unusual and we don't know what it is yet," that's honest reporting. It's not crying wolf. It's admitting uncertainty. The problem is that uncertainty doesn't make for good headlines. Media outlets want definitive answers. They want, "Scientists detect alien signal," or "Mysterious signal explained." They don't want, "Scientists detect signal, investigating, results inconclusive." So stories get sensationalized. Uncertain findings get presented as discoveries. Speculative hypotheses get presented as facts. And then, when the uncertainty resolves in a mundane direction, people feel let down. This is a communication problem. Scientists need to get better at explaining uncertainty to the public, at making it clear that investigation takes time, that most mysteries have mundane explanations, that the process of science involves a lot of dead ends, and the public needs to get better at accepting uncertainty, at understanding that science is a process, not a collection of facts, that it's okay to say, "We don't know yet." That mysteries are interesting precisely because they're unsolved. But there's another dimension to this, the existential dimension, the question of what it would mean if we detected an alien signal. For some people, it would be affirming, proof that life is common, that the universe is full of possibilities, that we're part of something larger. For others, it would be unsettling, a challenge to their worldview, their religious beliefs, their sense of human uniqueness. And for everyone, it would raise questions. Who are they? What do they want? Are they friendly or hostile? Should we respond? What should we say? These are profound questions. They touch on philosophy, ethics, religion, politics. They can't be answered by science alone. They require input from all of humanity, from different cultures, different perspectives, different belief systems. This is why the decision to respond to an alien signal, if we ever detect one, should be a democratic one, not decided by scientists alone, not decided by governments alone, but by humanity as a whole. Through international deliberation, debate, consensus building. It would be messy. It would take time. There would be disagreements. But it would be the right way to do it. Because this isn't just a scientific question. It's a human question. Maybe the most important question we'll ever face. Let me bring this back to the signals themselves. I want to tell you about one more mystery. The galactic center radio transient phenomenon I mentioned earlier. Let's dig deeper into this. The galactic center is about 26,000 light-years away. It contains Sagittarius A, our galaxy's supermassive black hole. The region around Sagittarius A is incredibly dense. Millions of stars packed into a relatively small volume. Some of these stars orbit the black hole at tremendous speeds. One star, designated S2, completes an orbit every 16 years. At closest approach, it's moving at about 3,100 miles per second, or 5,000 kilometers per second. That's almost 2% of the speed of light. These stars experience extreme gravitational forces. Time dilation affects them measurably. General relativity predicts that time runs slower in strong gravitational fields. For S2, at closest approach, time runs about 0.02% slower than it does for us on Earth. This has been measured. Astronomers have detected the gravitational redshift of light from S2. The light waves are stretched by the black hole's gravity, shifting them toward longer wavelengths. This confirms Einstein's predictions with extraordinary precision. But among all this activity, these stars whipping around a black hole, there are mysterious radio transients, brief flashes of radio emission that don't match any known source. They last for a few hours. They're bright, and they appear sporadically, unpredictably. One hypothesis is that they're related to magnetic activity on red dwarf stars. Red dwarfs are small, cool stars. They're the most common type of star in the galaxy, and many of them have powerful magnetic fields. These fields can store enormous amounts of energy. When the fields reconfigure, releasing that energy, they produce flares. Solar flares are a familiar example. Our sun has flares regularly. brief eruptions of energy that release as much power as billions of nuclear bombs. But the flares from red dwarfs can be much more powerful. Some red dwarf flares release as much energy as our sun emits in an entire day, concentrated into a few minutes. If a red dwarf near the galactic center flared, it might produce a radio transient. But the observed transients are brighter than expected from even the most powerful stellar flares, and they have unusual spectral properties. They don't quite match the model. Another hypothesis is that they're related to magnetic activity near Sagittarius A itself. The black hole's environment is threaded with magnetic fields. These fields interact with the infalling gas, channeling it, accelerating it, heating it. Sometimes, these fields might reconnect, releasing energy in a burst. This magnetic reconnection could produce a radio transient, but again, the details don't quite match. The transients are too bright. They occur too far from the black hole. So, the mystery remains. We have radio transients from the galactic center that don't fit any model. They might be a new type of stellar flare. They might be related to black hole activity. They might be something we haven't thought of. Or, and this is the most speculative possibility, they might be artificial. Could they be signals from a civilization that set up shop near the galactic center? The galactic center would be a strange place to build a civilization. The radiation levels are high. Supernovas are common. The tidal forces from the black hole are extreme. But maybe that's the point. Maybe an advanced civilization would be attracted to the galactic center precisely because of its extreme environment. Maybe they're harvesting energy from the black hole. Maybe they're using the black hole's gravity for some kind of massive engineering project. Maybe they're there because it's the center of the galaxy, a strategic location. This is pure speculation. There's no evidence for this. It's science fiction thinking, but it's worth considering. Because we don't know what motivates an advanced civilization. We don't know what they value, what they want, what they're capable of. Maybe the galactic center, with all its dangers and extremes, is actually an attractive location for a civilization that's mastered technology beyond our comprehension. Or maybe not. Maybe the transients are just stellar flares from unusual red dwarfs. Maybe we'll figure it out eventually, with better data, better models. But for now, it's a mystery. Another signal we can't explain. Another item on the list of phenomena that challenge our understanding. Here's what all of this comes down to. The universe is full of signals. Radio waves, light, gravitational waves, neutrinos. All of these carry information about their sources. Most of the time, we can decode that information. We can look at a star's spectrum and determine its temperature, composition, age. We can look at a galaxy's redshift and determine how fast it's moving away from us. We can detect gravitational waves and determine the masses of the black holes that produced them. Science has given us the tools to read these cosmic signals, to extract information from the universe, to understand what's happening in distant places. But sometimes, we receive signals we can't read, signals that don't fit our models, signals that suggest something new, something unknown, and those signals are precious. They're opportunities. Opportunities to expand our knowledge, to discover new physics, new astronomy, new phenomena, or, just maybe, to make contact with another civilization. The search for these signals, the investigation of these mysteries, is one of the most important endeavors in science. It's not just about aliens, though that would be extraordinary. It's about understanding the universe, about pushing the boundaries of what's known, about asking questions and seeking answers. And it's about being humble, about recognizing that we don't know everything, that the universe can surprise us, that there are phenomena out there we haven't imagined yet. Every time we detect a mysterious signal, we're reminded of this. Reminded that the cosmos is vast and strange and full of wonders, and that we're just beginning to explore it. So when you hear about a mysterious signal from space, don't dismiss it. Don't assume it's nothing. But don't assume it's aliens either. Approach it with curiosity, with openness to possibility, with rigorous skepticism, with a willingness to investigate thoroughly before jumping to conclusions. That's the scientific approach. And it's the approach that's led to every major discovery in the history of astronomy. Pulsars were discovered by investigating an anomaly. The cosmic microwave background was discovered by investigating noise in a radio antenna. Exoplanets were discovered by investigating wobbles in stellar motion. Dark energy was discovered by investigating dimmer-than-expected supernovas. Every discovery starts with a mystery, with something that doesn't fit, with a signal that shouldn't be there. And the mysterious signals we're detecting today might be the seeds of tomorrow's discoveries. They might lead to new understanding of neutron stars, black holes, galaxy formation. They might reveal new physics, new forces, new particles. Or they might lead to the most profound discovery of all. Proof that we're not alone. That somewhere out there, in the vastness of space, another civilization is transmitting, sending signals into the void, hoping, just like we are, to make contact, to find out if anyone else is listening. And if that day comes, if we detect a confirmed alien signal, it will be because we kept listening, because we investigated every mystery, because we took every anomaly seriously, because we refused to assume we already know everything. The universe is speaking to us, in radio waves and light and gravitational ripples. Most of the time, we understand what it's saying, but sometimes the message is unclear. The signal is mysterious. The meaning is hidden. And those moments are when science gets interesting, when we're forced to think harder, to look closer, to question our assumptions. Those moments are when discoveries happen. So here's my final thought. The mysterious signals we keep receiving from space are not just scientific curiosities. They're not just data points to be catalogued and analyzed. They're messages from the universe. Reminders that there's more out there than we know. More to discover. More to understand. And every time we detect one, every time we investigate, every time we ask, "What is this?" we're engaging in one of humanity's most noble pursuits. The pursuit of knowledge. The search for truth. The exploration of the unknown. That search continues. Every night, telescopes scan the sky. Every day, computers analyze data. Every week, scientists publish findings. And slowly, methodically, we're expanding the boundaries of what's known. We're cataloging pulsars. We're characterizing FRBs. We're mapping the galactic center. We're listening for alien signals. And we're finding mysteries. Signals we can't explain. Not yet. But we're working on it. We're building better telescopes. We're developing better algorithms. We're training new scientists. We're asking better questions. And someday, maybe in our lifetimes, maybe in our children's lifetimes, maybe centuries from now, We'll solve these mysteries. We'll understand what's producing these signals. We'll decode the messages the universe is sending us. And we'll know, finally, whether we're alone, or whether the cosmos is full of voices, full of civilizations, full of minds looking up at their own skies and wondering the same things we wonder. Until then, we listen, we investigate, we keep searching, because that's what we do. That's who we are. We're the species that asks questions, that seeks answers, that looks at a mysterious signal and says, let's figure this out. And as long as we keep doing that, as long as we keep listening, keep searching, keep wondering, there's hope. Hope that we'll understand. Hope that we'll discover. Hope that we'll find what we're looking for, or find something we never expected. Something that changes everything we thought we knew. The search continues. The mystery remains. And the universe keeps its secrets. For now. Good night.